Hello, welcome back again. So last time we got a lot of our setup done for creating our graphics pipeline. Well, some of our setup done, should I say. We went through, created our shaders, we created the shader compiler. We then loaded the shaders into memory, and then we created that little wrapper of the shader module over those shader binary formats. Then stopped it there, but then realized that we're actually at the last small stage of just pretty much just copy and paste. So I figured come back on, do a little bit more, and then jump into the fixed functions after these shader modules. But I don't think, we still are really early on in our graphics pipeline, so there's more to come. So one quick thing I wanted to do is wanted to update is when we call malloc here, not here, sorry, in our file open function here, we then don't free it. I think we're just relying on this to free the actual fragment shader module, but there's no guarantee that it's going to free up that, at least as far as I'm aware, there's no guarantee it's going to free up the actual space that we malloced onto the heap. So I know we're already going to quit our program and the OS is likely to clean that up for us, but it's always good to clean up after yourself. I also want to rename this to just Vert Shader and Frag Shader, because it actually isn't just the code anymore, it's some other stuff. It's the size. Right, okay. So what I want to do is take our Vert Shader and in our cleanup, I want to call free on Vert Shader. It's just dot code, and also on our frag shader code. And I just want to see if that kills anything or if that actually works fine. All right, quit it, and I think it works fine. Run it again. Yeah, okay, I think that does work fine. So at least we're being a bit more explicit that we're cleaning up our malloc, our memory allocation, and then we are doing our cleanup of any Vulkan any VK/Vulkan assets or memory allocations or whatever. Okay, moving on. So we're on to the shader stage creation. To actually use the shaders, we will need to assign them to a specific pipeline stage through the VK pipeline shader stage create info structure as part of the actual pipeline creation process. We'll start by filling in the structure for the vertex shader again in the create graphics pipeline function, which is the one that we're in here. Let's just copy and paste this. Not really sure what accent that was. Sorry to anybody that might offend. Right, we are just creating these two items on the struct, and there's more to come. First step is, besides the obligatory S-type member, is to tell Vulkan which pipeline stage the shader is belonging to. Is going to be used. Sorry, there is an enum value for each of these programmable stages described in the previous chapter. Oh yes, those are the orange, although I thought they were yellow, pipeline stages. And we are going to put it into the shader stage. Oh wait, that's the S-type. The stage, so it is the vertex shader. Okay, vertex bit. Okay, then we need to do this. The next two members specify the shader module containing the code, which is the one we created before with this thing here. And its entry point. Oh, so the main function. All right, cool. So add those to our struct. So its main is the name of the function, which is the entry point. There's one more optional member, p specialization info, which we won't be using here, but it's worth discussing. It allows you to specify which of the shader constants Okay, so these are the things that make it specifically dynamic, so you can pass in a bunch of constants that the shaders can then use before they're compiled. Wait, doesn't make sense. Maybe the binary code waits for those or something. You can use a single shader module where its behavior can be configured at pipeline creation. As pipeline creation, and when the creation we do the loading, so we can do the compilation at the same time as the loading or the creation. Where were we? Yes, specify blah, blah, blah. This is more efficient than configuring the shader using variables at render time, because the compiler can do optimizations like eliminating if statements that depend on these values. If you don't have any constants like that, then you can just use null pointer. All right. Do we want to explicitly put that in? It's just like null. Okay. Modifying these structures to suit the fragment shader is easy. Oh. Are we actually going to do that? Okay. Let's not do that. I'll just comment that out for now. I'm not sure if we are expected to do that. All right. Whoops. Okay. Yep, that looks good. Finish by defining an array that contains these two structures, which we'll later use to reference them in the actual pipeline creation step. All right, so those two structures are going to be in here. Let's give an extra bit of space here because I think this stuff needs to be at the very end of this function. Yeah. All right. What are you? Just because you're not being used. Yes. All right. Cool. Moving on. Let's just check that actually compiles and that everyone is happy. It does, and they are. Cool. Fixed functions, dynamic state, vertex input, input assembly, viewports and scissors, rasterization, multi-sampling, depth and stencil testing, color blending, pipeline layout, and conclusion. This is, well, it looks big, but it's not that big at all. The older graphics API has provided default state for most of the stages in the graphics pipeline. In Vulkan, you have to be explicit about most pipeline states even, as it'll be baked into the immutable pipeline state object. In this chapter, we'll fill in all the structures to configure these fixed function operations. Okay, for dynamic state, while most of the pipeline state needs to be baked into the pipeline state, a limited amount of that can actually be changed without recreating the pipeline at draw time. Examples are the size of the viewport, line width, and blend constants. Oh, okay. So if you've already defined a pipeline, we can change a couple of things at least. If you want to use dynamic state and keep these properties out, then you'll have to fill in a VK pipeline dynamic state create info struct, like so. Let's do that, but let's DC++ify it like this. This is just going to be a dynamic states thing. I like to put that on one line. And this is going to be a struct. And we're not going to use this dynamic state size. We have to create this variable. And cast is going to just be a static cast. UN32T, okay. U32. And we already know the size is 2. I believe. I think that's probably right. We don't need .data. We don't need that. Wait, we don't need that. We don't need that. All that. All right. Why are you complaining about something? Oh, because you need to be not a pointer, you're actually that. Alright, now. This will cause the configuration of these values to be ignored, and you will be able to, and required to, specify the data at drawing time. This results in a more flexible setup and is very common in things like viewport and scissor state. Which would result in a more complex setup when being baked into the pipeline state. Vertex input. The VK pipeline vertex input state blah 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 struct describes the format of the vertex data that will be passed to the vertex shader. It describes it roughly in two ways: bindings, space between data, and whether the data is per vertex or per instance. See instancing. Attribute descriptions, which is the type of attribute passed to the vertex shader, which binding to load them from, and at which set offset. Because we are hard-coding the vertex data directly into the vertex shader, we'll fill in the structure to specify that there is no vertex data to load for now. We'll get back to this in later chapters. Okay. There's a lot of copy and pastas. Pasta. Oh, didn't need to put that. Whoa, jumping around. That is optional. That is optional. That is not a null pointer. It's just this. And we want to close that struct off. And we want to ditch that. Hey. All right, that looks correct. The p-vertex binding descriptions and p-vertex attribute descriptions members point to an array of structs that describe the aforementioned details for loading vertex data. Add the structure to the create graph. Oh, we already did. Right after the shader stages. Oh, we did not. We added it down here. Okay. Let's add it here. Input assembly. The assembly state create info. Struct describes two things: what kind of geometry will be drawn from the vertices, and a primitive restart should be enabled. I don't know what that is. The format is specified in the topology member and can be values like topology point list, topology line list, and line strip, as well as triangle list, triangle strip. Normally, the vertices are loaded from the vertex buffer by index in sequential order, but with an element buffer, you can specify the indices to use yourself. This allows you to perform optimizations like reusing vertices. If you set the primitive restart enabled member to VK true, then it's possible to break up lines and triangles in the strip topology, in the strip topology modes by using the special index of those hexadecimals, or whatever basic C thing. We intended to draw triangles throughout this tutorial. We'll stick to the following data structures to just draw triangles. Okay, probably below here again. All right, and get rid of all this and redo these. Okay, viewports and scissors. A viewport basically describes a region of the frame buffer that the output will be rendered to. Yep, that makes sense. This will always be 0, 0 to width height, and it is in the tutorial also the same case. But what's a scissor? I don't know, but you shouldn't run with them. Sorry, I'm so sorry everyone. Okay. Get rid, oops, didn't mean to delete all that. Oh, swap chain extent. That is in our P app, I believe. Yes, it is. And let's cast it without doing a space. That looks good. These are our floats. Yep. Remember that the size of the swap chain and its images may differ from the width and height for the window. Yes, we read that out a few chapters ago. The swap chain images will be used as frame buffers later on, so we should stick with their size. The min depth and max depth values specify the range of depth values to use in the frame buffer. These values must be written as floats of 0.0 to 1.0. But min depth may be higher than max depth. If you aren't doing anything special, then you should stick with the standard values. Okay. While viewports define the transformation from the image to the frame buffer, scissor rectangles define which region's pixels will actually be stored. Any pixels outside the scissor triangle will be discarded by the rasterizer. Scissor rectangle, sorry, not triangle. They function like a filter rather than a transformation. Okay, the difference is illustrated below. Note that the left scissor triangle, triangle? I keep reading that. Rectangle is just one of many possibilities that would be in the image. Okay, that's cool. So the viewport stops around here, like midway. So we see what's in the viewport availability. If the whole thing is in the viewport, but the scissor rectangle is only here, then that kind of makes sense. Okay, so it's kind of like a mask. Kind of, not really. So if we wanted to draw to the entire frame buffer, we would specify the scissor rectangle that covers it entirely. Like this, yep. Okay, we do want to do that, so let's do that. Oh, again, that is our p-app, subchain, extent. Viewports and scissor triangles can either be specified as a static part of the pipeline or as a dynamic state. Excellent. Ooh, so you can do fancy effects to like James Bond thing. What a horrible person. While the former is more in line with the other states, it's often convenient to make viewport and scissor state dynamic as it gives you a lot more flexibility. This is very common and all implementations can handle the dynamic state without performance penalty. Oh, one of those zero cost abstractions we keep hearing about. When opting for dynamic viewports and scissor rectangles, you need to enable the respective dynamic states for the pipeline. Did we already do that? Where's our dynamic states? We have viewport and state scissor. Yeah, we did that. And we did indeed do that. Type pipeline dynamic state create info, type pipeline dynamic state create info. Dynamic state size, and the data. Yeah, we did that. And then you need to specify the count at pipeline creation time. Did we do that? No, we didn't. Okay, so let's do that. After we've done our viewport and scissors. Okay. Whoops. Little trigger happy there. So viewport state. All right. The actual viewports and scissor rectangles will then later be set up at drawing time. With dynamic state, it is even possible to specify different viewports and or scissor rectangles within a single command buffer. Without dynamic state, the viewport and the scissor triangle need to be set in the pipeline using the VK pipeline, blah, 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 blah. This makes the viewport and scissor triangle for this pipeline immutable. Any changes required to these values would require a new pipeline to be created with the new values. Okay. Independent of how you set them, it is possible to use multiple viewports and scissor rectangles on the same graphics card. So the structure member references in arrays of them. Whoa, hang on, that was hard to read. It is possible to use multiple viewports and scissor rectangles in some graphics cards. So the structure members reference an array of them. Okay, that's fine. Using multiple requires enabling a GPU feature. See logical device creation. So are we doing that? in the viewport state? I think probably are. Let's just copy those again. Okay, get rid of these. Okay, so we're creating our scissor dynamically and our viewport dynamically because we stated it in here. And then we do send the pointer to them so we can change them at render time whenever we like. Okay, excellent. Rasterizer, come on, we're nearly sort of ish there. Rasterizer takes the geometry that is shaped by the vertices from the vertex shader and turns it into fragments to be colored by the fragment shader. It also performs depth testing, face culling, ooh, that sounds rough, and the scissor test. Yeah, so whether it's outside or inside the scissor rectangle. Scissor test, I like that. And it can be configured to output fragments that will fill entire polygons or just the edges wireframe rendering. All this is configured using this. That's cool. All right. I feel like we should be annotating some of this or something. Okay. If depth clamp enable is set to VK true, which it isn't in that thing, then fragments that are beyond the near and far planes are clamped to them, as opposed to discarding. Oh, okay, so there's like a maximum boundary. This is useful in some special cases like shadow maps. Yeah. Using the required enabling GPU features, okay. We're not gonna do that. So we have to, oh no, that's something different. If rasterizer discard enabled is set to true, then geometry never passes through the rasterizer stage. This basically disables any output of the frame buffer. We don't want that, that's for sure, no way. So in a rasterizer, let's put that to false, because we would like some output, that'd be pretty handy. And then similarly, what's this one? The polygon mode determines how fragments are generated for geometry. The following modes are available: polygon fill, line, point. That kind of makes sense. And it requires GPU stuff yet again. Alright, seeing a pattern emerging here. Dot line width is 1.0 float. The line width member is straightforward. Yeah, I can figure it out. Wide lines. Then we have cull mode and front face within the same thing. Which we are setting here. Okay. Cull mode variable determines the type of face culling that is used. Disable culling, yeah, okay, it's fine. The front face variable specifies the vertex order for faces to be considered. Front facing, so clockwise, okay. Clockwise or counterclockwise. Then there's these other ones, these last ones. Here you go, here's the last of the last. Wrong key to copy. Alright. So we have the rasterizer can alter the depth values by adding a constant value or biasing them based on a fragment slope. Slope factor, okay. This is sometimes used for shadow mapping, but we won't be using it. Just set it to VK false. Okay, now multi-sampling. The VK pipeline multi-sampling state create info struct. Excuse me, configures multi-sampling, obviously, which is one of the ways to perform anti-aliasing. So we're smoothing out the edges of pixels. This works by combining the fragment shader results of multiple polygons that rasterize to the same pixel. This mainly occurs along edges, which is also where most of the noticeable aliasing effects happen. Okay, blah, 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 blah. Enabling it requires a GPU thing. Okay, fair enough. Let's just get cracking. These are all just copy and pastas. Up. Get rid of that. Get rid of that. Get rid of that. That is null. That is VK false. And that is VK false too. Then we close out that. And yep, that all looks good. All right. Now we'll revisit multi-sampling in a later chapter. For now, let's keep it disabled. Depth and stenciling testing. Are we near the end of this? This is getting... Ooh. Close. Oh, I didn't mean to do that. No. All right, here we go. Depth and sensor testing. Blah, 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 blah. Kettle blending. Don't have one right now, but we can simply pass a null pointer as the endpoint. Okay. Let's see. I wonder if we actually need that. Take a look at that code in a bit to check if we need that. And I'll put it here. Just in case that's required. Gosh darn it. Okay. Moving on to color blending. After fragment shader is returned, God, I'm just going to copy and paste this stuff because there's a lot to read, and I think we can all agree that reading it in our own time is probably better than watching me try and read out loud to you folks. Less than interesting episode, unfortunately. But as is mentioned in this tutorial many times, there's a lot of setup for a lot of this Vulkan stuff. And it seems as though the rendering pipeline is no exception. Alright, so that's that one ready. The pairframe buffer struct allows you to configure the first way of color blending. Oh, okay, this is quite interesting. So we can decide if we want to do like subtraction, addition, multiplication, that kind of stuff. The operations that will be performed are best demonstrated by using the following pseudocode. Yes. Final color is the first color multiplied by the new color. Well, it's not some kind of source blend. Okay, blending factor. Yeah, this is describing how we want colors to interact with each other. If blend enable is set to VK false, then the new color from the fragment shader is passed through unmodified, so it's just like straight up overlay. Otherwise, the two mixing operations are performed at compute to compute a new color. The resulting color is ANDed to the color right mask to determine which channels are actually passed through. The most common way to use color blending is to implement alpha blending, where which changing the opacities with the old color and opacity. Yeah, okay, so final color. What is that? Oh, that's more pseudocode. Okay, so we have this color blend attachment. Let's add some more of these. Wait, they've already got them. This can be accomplished with the following parameters. Do we want to do that? I kind of want to look at their code to see if that's what they did. What did you do? So they, oh, did I even copy that? They had to false. Okay, so we'll just follow their thing. Oh, tell you what I should have done. Also checked if they had this. It did. Oh, so do we. Why do we think we didn't need it? I don't know. Okay, all that. Moving on. More color blending S-type. Oh, this is another struct. Okay. Oh, sorry if this is less than fun, folks. Sometimes you just gotta go through drudge work as a programmer. Sometimes you gotta go to the wrong screen as a programmer. Okay, right. At least we're all gonna be on the same page. Right. There you go. This is what you want to use a second method for blending bitwise combination. Then you should set. Yeah, okay. We're just gonna stick with the default. I'm sure we'll come across all this stuff later on. Now, pipeline layout, final bit, apart from the conclusion. Penultimate, you can use uniform values in shaders, which are global, similar to the dynamic state variables that can be changed at drawing time to alter the behavior of the shaders without having to recreate them. They are commonly used to pass the transformation matrix to the vertex shader, yes, or to create text samplers in the fragment shader. Right. These uniform values need to be specified during pipeline creation by creating a VK pipeline layout object. Even though we'll be using them until the feature chapter, we will still be required to create them as empty layout. Okay. Create a class member to hold this object. Oh, class member, so back on our app. And then create the object in the create graphics pipeline function. All right, let's just go do this first. I'll copy all of that even. All right, so got all this. Let's go up to here. All right. Kill all those. That isn't a thing. The null pointer is just straight up null. Same with that. Let me just check if I haven't copied that somewhere else. I have right here. That's it. Okay, pipeline layout, which is going to be also on our, well, they're using it as a class member, but we are not. P-app. And we don't do this, we actually do printf and then exit with, are we on 8 yet? Nope, must be on 7. All right, now back up to our app where we have a VK pipeline layout called pipeline layout. Excellent. And there it is there. So we should be error free. Oh wait, hang on. The structure also specifies push constants, which are another way of passing dynamic values to shaders. There's quite a few ways of doing that. That way we get into a feature chapter. Okay, that's fine. The pipeline layout will be referenced throughout the program's lifetime, so we should be destroying it at the end. Yes, you're probably right, we should. Let's go to our cleanup. And where should we call it? Right at the start, evidently. Passing in null and a p-app, pipeline pointer, and our device. Right, now let's try and compile, see what is wrong. Nothing at all. Everything works great. Right, slug through that pretty well. That's it for all the fixed function state. There's a lot of work to get all set up from scratch, but the advantage is that we're now nearly fully aware of everything that is going into our graphics pipeline. That is true. I like that kind of control. This reduces the chances of running into unexpected behavior because the default state of a certain component is not what we expect. Yes. There is, however, one more object to create, of course, before we can finally create a graphics pipeline, and that is a render path. So let's go to the render pass, but let's also leave that for another video because this is already quite long. Git status, git add main, and git commit. 2 M's in the word commit, in case you didn't know. Oh. Right. Finished. No, we didn't finish anything. Oh no, we did. Fixed function. How do we call that? Fixed function setup. Let's call that. Git push origin main, and that is a wrap for today. Thanks very much for watching me copy and paste and complain about it. See you next time.